So most welcome to the Royal Swedish Academy of Sciences and this two-day symposium of research perspective of the security and preparedness in the climate change in the Arctic. And this symposium has been organized together with the Royal Swedish Academy of Sciences and the Norwegian Scientific Academy for Polar Research. And we appreciate that so many of you could come here and to meet physically for scientific discussions and presentations. And also nice that we can be here in this hall that is newly renovated, and the light sitting here even got a prize. And the topic of the symposium today is really important, it's interesting, but also very timely, especially considering the turbulent world that we are living in, with warming of the climate, but also the geopolitical situation, with the war in Europe, in Ukraine, but also with the big climate meeting, COP27 in Egypt, ongoing for the moment. Humankind is one single species that has influenced and influences the environment enormously. And it's essential for us, but also for the generations to come, that we take care of our planet in the best way and reduce climate changes. Research on climate change is instrumental for us to understand what is coming and what can be done to change this rapid development. And there need to be academic freedom to investigate relevant and important research questions, as well as we have access to available data and the infrastructure needed for the research. And the Royal Swedish Academy of Sciences has four main goals. Namely, to promote science, and that you can do by awarding, for example, prizes. As you know, we are awarding the Nobel Prizes in physics and chemistry, but also the Economy Prize in the memory of Alfred Nobel. But also to build a scientific ground for evidence-based political decisions, what we call science for policy. As well as to strengthen the terms for research as such, but also, of course, to be a meeting place for scientific discussions and seminars. And our academy has a long-standing engagement in different global sustainability issues, such as climate, energy, but also human health and inequalities. And we give advice to policymakers and stakeholders. So this symposium and the topic that we will hear about today is really well in line with the goals of the academy. So by that, I wish you all most welcome once more. And I hope that you will have two fruitful and really exciting days discussing climate changes in the North. And by that, I will give the word to Leif here for introduction.
Yeah, I also like to welcome you all to this symposium. But before I start my introduction, I should give you some warning words here. As you can tell or hear, it's very good sound conditions here, and that's because there's a lot of microphones up in the ceiling here. And these microphones pick up whatever you're saying. And as this session is also streamed, so if you say something, just whisper something, that will be going all over the world, so be careful what you're saying. Okay, I'm a retired professor in marine chemistry at Gothenburg University. And much of my scientific life has been dealing with studying the carbon cycle in the high latitudes, mostly the Arctic Ocean. And this has taken me to a lot of field trips up in the Arctic. And the first trip was in 1980 on the icebreaker Ymer. And these were in the waters around Svalbard, and we met a lot of multi-year thick, up to 4 meters thick sea ice. Here you can see, I don't know if you, at least to the left there is a photo where the bow propeller has machined a piece of the ice there. It's 2 meters in diameter, that machining the propeller. And it was very heavy ice conditions. And these ice conditions were prevailing during most of the 80s and also much into 1991 when we had the first cruise on the new icebreaker Odin. There were a lot of big ice floes, multi-year thick, more than 2 meters thick ice, with leads in between, different thicknesses. And we managed to get through all the way up to the North Pole in these leads. But my first experience of dramatic change was in 1996, when we came up roughly halfway between Franz Josef Land and the North Pole. We had a lot of open water. There were big lakes. I mean, there were sea ice to the south, but we were steaming in big lakes for hours. And then in 2014, that was my last cruise on icebreaker Odin. And this photo is when the sea ice is starting to freeze again in September. And we sailed from Siberia up to roughly 84 degrees north in open water. And this was a little bit scary. I mean, these were areas that a few decades before had been covered by multi-year 2 meter thick ice. And so this is very dramatic changes. So the people who don't believe in Arctic climate change, they can come and talk to me, because I've seen it myself. But even better so, come on. They can read this report, this IPCC report, the Ocean and Cryosphere in a Changing Climate. This was produced in 2019, and they give a lot of examples of other changes than just the sea ice conditions. And the report was also what inspired us, that is the Norwegian Scientific Academy for Polar Research, and the class for geosciences at the academy here to arrange this symposium. And as you probably, or we might know, we planned to have this symposium roughly 1 year ago, but due to COVID and the restrictions of having meetings on site, we had to postpone it, because we wanted to have it in real time so we could have fruitful discussions. And having this delay in 1 year of this symposium has made this topic even more important, sadly, I must say, because we know, as Birgitta said, we have experienced a lot of changes to the political situation here now. So I'm really looking forward to the discussions and the presentations from the speakers, and I thank you all to come here, especially the speakers and the moderators. And now I will give the word to Paul Wassmann, who will start this. We start the first session. We have these 5 sessions, as you've seen in the program, and he will take the lead on the first session. Please, Paul.
Thank you very much for the invitation to moderate this session. This session is entitled Access to Infrastructure and Data for Arctic Research. And given the extent of the Arctic Ocean and the big climate changes and the few vessels which usually steam up there, the need for data exchange and infrastructure and technology is very timely. And I will not use so much words about that. You may know about that, so I will introduce the first speaker immediately, which is Katarina Gårdfeldt from the Polar Research Secretariat in Luleå, and she will talk about polar research infrastructure, a bridge to international cooperation. Please.
Thank you, Paul. Thank you very much. And warm thanks to the organizers to invite me here to this session. My name is Katarina Gårdfeldt. As Paul said, I'm Director General for the Swedish Polar Research Secretariat up in Luleå. And do I change here? Yes. Okay. So first I would like to say a few words about our secretariat and the mandate that we have. The Swedish Polar Secretariat's mission, it's quite strange. One must stand at this point here, so okay, I will follow the rules that we heard from Peter. The Secretary's mission is to promote and coordinate Swedish polar research and to follow and plan research and development, and also to organize and lead research expeditions, create favorable conditions for polar research without field work. We also are experts to the Swedish government, since we are a governmental agency. In Norwegian, I think you call it the Directorat. So we are expert for the Swedish government in different international negotiations and partnerships, and we also represent Sweden in polar matters. We issue permits according to the Swedish Antarctic Ordinance. That means that Swedish citizens who want to go Antarctica, they have the permission via us. So we operate in the polar region. We are quite a small agency with a very large parish, I would say, from the north to the south. We have infrastructure both in Arctic and Antarctica, and we have also a station in the mountain areas, which is a subpolar area. And the infrastructure that we organize is the Abisko Scientific Research Station in the Swedish mountain, which was a gift to us from the Royal Academy of Sciences around 12 years ago. We have Vasa and Svea in Dronningmordland on East Antarctica continent, and we have the icebreaker Oden, which will be most in focus during this presentation. So this is just a picture of Abisko Research Station. It has a very it has the surroundings of very high variability. It's located near the Lake Torneträsk. We have the high mountain area, we have glaciers, and it's a very variable area for researchers to come to study different processes. And it has a leading international climate and research. Almost 600 researchers yearly are coming to the station. And it's popular around international researchers and Swedish researchers. Vasa and Svea on the Antarctic continent is only a summer station. Abisko is open full year, but those two stations on Antarctic are only summer stations. This means that my colleagues are going down there now during this month and open the station for the researchers. If you want to have more information about the research on our station, you're welcome to visit the website where we have the timetable Vasa, and there the research that is conducted down there is more explained. It's a nice location because we have nice neighbors. It's very close to the Finnish station Ahua. And here is our flagship, I would say, the icebreaker Oden. She is one of the world's most powerful icebreakers. She has 4 engines, 24 horsepower. And she has been used for scientific work in the Central Arctic Oceans since 1999, I think. 91, yes, when Leif Andersson was one of the first scientists on board. She has been to the North Pole 10 times since then. She was the first non-nuclear power civil ship that went to the North Pole, actually, together with the German vessel Polarstein. And she's owned by the Swedish Maritime Administrations, but the expeditions are organized by us. Alongside with the expeditions on board Oden, we also have the Teachers Program and the Artists Program. And outcomings from the Artists Program was actually a basis for research expeditions at Museum Valdemarsudde last year. It was called Expedition Art. So polar science in Sweden. We have not only, so to speak, hard infrastructure, we also have this, what we could say, soft infrastructure. It's a network of polar scientists. We think that it's very important to help scientists to find each other and also to showcase that polar science in Sweden is actually it's big, but it's growing. So we wanted to show that there is a critical mass of polar scientists and that they could easily find each other and even make the subject more popular among young scientists to make a career on. So the polar researchers in Sweden, it's a public searchable list with the polar researchers in Sweden. It was launched by us at our website in 2029. And currently 110 researchers, and the network is growing. It markets the researchers and shows the breadth and the depth of Swedish polar research. It facilitates the Secretariat's communication with the researchers, and we sent also out a newsletter to these people to keep in contact. And it's a way of researchers and others to find polar researchers in Sweden. And you can filter by region, university, areas of expertise, and also use a free text search. And each researcher, I will soon show you, has a profile card with the summary information, including which SDG in the Agenda 2030 that the researcher's research is most devoted to, and also a link to their professional site. So this is how it looks if you go to our website. You can do a search for something, an area for Central Arctic Ocean, for example, and then it will pop up researchers working with that. And this is an example of how it looks like, and you can see that this professor at Stockholm University, his research is much related to 4 of the Sustainable Development Goals here, and we have also made some statistic about the goals that the researchers work with so far. And you can see that polar research cover the front line of Agenda 2030, I would say, with a big emphasis on goal number 13, climate action, 14, life below water, and also 15, life below land. But goals as peace, justice, and strong institutions are also well represented. And for us, I think it's very important to show that polar research is really relevant for Agenda 2030 and the societal challenges that we have. So please, if you're not a part of the network and interested, please go to our website and become a member. So we are a small agency with a large parish, as I said. So our method to get something done is to work with partnerships. We work with the Swedish Research Council and try to harmonize our efforts with the funding that the researchers get at the universities. Of course, we have a partnership with Swedish Maritime Administration, the owner of the Oden, Swedish National Space Agency, SMHI, the Swedish Meteorological and Hydrological Institute, Swedish Agency for Marine and Water Management, Havmyndigheten, Geological Survey of Sweden, and the university, national and international, is of course one of the core partners that we work with. EU funds some of our work, and we are active in some projects, and other national and international organizations for polar science, and also we have a global network of researchers. So now we will go into the focus of the presentation, where I will try to showcase that marine infrastructure actually is a bridge for international collaboration. And in these days, I think this is more important than ever. And I will show some example that we, Swedish Polar Research Secretariat, have experienced with expeditions with icebreaker Oden. And one very impressive effort is the Synoptic Arctic Survey expedition. That was an effort by scientists. Again, Professor Leif Andersson was one of the initiators, together with many other scientists globally. It's a bottom-up process. And during this expedition, Oden was one of 12 ships, not just icebreaker, but marine research ships that has been to the Arctic Ocean and map in a very organized way different parameters that is important to understand for climate change and the effects that have on the Arctic Ocean. So the expedition was organized under 3 major research areas. You can see them here: physical drivers and importance of the ecosystem and carbon cycle, the ecosystem response, and the carbon cycle and ocean acidification. And during 3 years, 12 ships are doing a common effort here. And I think it is impressive to see that scientists, through a bottom-up initiative, can organize such a big effort. And we try to do what we have been inspired by this way of working at the Polar Research Secretariat. And we have invented a process that we call the Polar Research Process, which is an invitation to an innovative, hopefully, multidisciplinary and global coordination of polar science. It comprises 7 steps. Step number 1 is a bottom-up process for suggestion of research themes. And here we go out to the research society with a broad call and ask the researchers within Sweden with their international contacts to suggest themes for research, polar research, that also includes an expedition with the icebreaker Oden or the use of other infrastructure that we have at the Secretariat. Then we have a prioritization of these research themes with a peer review group that we put together. After that, we have a call for application within these prioritized themes, and then we have execution of the successful applications that has been selected for the specific call. And we have an expedition, we have field going, but we have also research within the theme, but outside expeditions. This means that scientists from a very broad scientific community are welcome in very many different areas, not only research that must go into the field. And then we have the researchers, of course, themselves, they produce disciplinary publications, but we ask them to join a process which we call research to policy, where a multidisciplinary synthesis report will be created. And this report we will use to present to decision makers and so to help the process of informed decisions in the societies. You can go into our website and see more about this. So the statistic from the first round of this call for Polar Research Process were 7 large transdisciplinary or multidisciplinary themes. The main applicants, of course, was from Swedish universities. This is mandatory because we are Sweden's agency. There were 115 applicants, 102 unique. This means that some scientists were participating in more than one theme. 29 international departments and 9 different countries were represented. So this is one of the points that I wanted to make, that polar science actually is a bridge for international collaboration. And from this call, we have made this tentative timetable for icebreaker Oden. 3 themes were selected. And because of the war in Ukraine, because of Putin's war in Ukraine, we have been forced actually to postpone and stop planning for 2 expeditions. The ARCOP that was supposed to go this summer to the Lomonosov Ridge was stopped. Because of the founding body on the European level didn't find the site where we were going secure enough for researchers. So the planning for that expedition has been stopped. And very sadly, also we have stopped the planning for the Eurasian Arctic Shelf Basin Interaction of Climate Cryosphere Carbon Contaminants, the C4. This was a very high-ranked theme from the Polar Research Process. Professor Örjan Gustafsson and Birgit Will at Stockholm University was the main applicants, but we have had to stop or postpone this because this expedition was planned to go to the Siberian shelf in Russian economic zone and in Russian waters. So this is very sad, and this is a consequence of the war. But we have still two themes left. The first one here is Art of Melt. Professor Mikael Tjernström and Paul Seeger, both at Stockholm University, is the main theme applicants here. And it will be conducted this spring, 23. And we have the Northern Greenland Earth Ocean Ecosystem Observatory. Main applicants for that team were Professor Martin Jakobsson here and Nina Kirchner. And these two expeditions are still in planning. And you can see that they have come differently far in the planning process. Art of Melt has already gone through the step number 4, which is call for applications. And this is a very short picture of what the Art of Melt expeditions will be about. We will deploy Odin in the marginal ice zone, and during coffee break I think you can talk to Mikael Tjernström more about the scientific goals of this very expedition. From the planning process of Art of Melt, I would like to show by this slide that it has been very successful for international collaboration. You can see all the countries and all the young universities that has been within the planning process and also been in our workshops. Norway, Denmark, Finland, US, UK, Canada, France, Switzerland, Germany and Sweden. I think this is a very nice way of showing that themes that Swedish researchers suggest in this bottom-up process is actually very successful for international collaboration and co-financing, actually, because that is also an important part in doing research expedition.
5 minutes left.
5 minutes left, okay. GeoEO, this is also in the planning for 2024. We have Martin Jakobsson here. Please talk to Martin about I think you can do it much more elegantly than I can. So please talk to Martin about what this expedition will be about. But also here we see that it has a great breakthrough internationally, and we have actually so many projects and so many top researchers that want to join that we will have a really hard time to select. Okay, we also work with a research consortium within Horizon, and it's a consortium for Arctic research icebreakers. And we had a call for ship time for transnational access. And that was also quite successful for us. You can see that on board research vessel Odin, 7 researchers from Germany, 4 from Germany and 2 from UK, was successfully and could join the SAS expedition with EU financing. And also you see all the other. Kronprins Haakon had 5 successful applicants from Denmark which could join through EU funding, and this is also promising. What about the future? I hope I can do this in 5 minutes, but we have really, I say this first, we have really a lack of heavy icebreakers, and I will try to get you to really agree with me. Because you heard in news, and so there are many countries are building research vessels now that can go to the Arctic and so on. In an, I would say, opportunistic way, because if it's open water, like Leif said, then it's not a big deal. But if you don't want to do it in an opportunistic way, if you want to do it in the planned way, if you look for the ice, if you look for the winter season and so on, you really must have a heavy icebreaker. Therefore, I think it's very important to know the discrimination between icebreakers, ice-breaking vessels, and ice-classed vessels. And I do not have the time to go into that, but you can look at the ARISE report later on. We have tried to sort this out, because in the left part of the diagram, you see International Maritime Organization Class A. It's quite broad, everybody fits in there, but it's a great difference between the vessels there. Then you have code B and C, but the ships are the ships have been gone through the different regulating bodies according to the classification that they have on a more detailed level than just A, B, and C. And here, this is a hobby that we have at the Research Secretariat. It's to put the icebreakers worldwide in a diagram. And you can see at the strongest icebreaker, it's Oden, Kronprins Haakon, and Polarstern, Amundsen. US has an own classification system, but they have also very strong icebreaker. Polarstern is a new vessel and a very welcomed contribution to heavy icebreakers. But Oden, for example, are old, Polarstern are old, and so on. So the new built vessels that you can see here, they are okay, they are IMO A icebreaker, but they are much weaker and cannot do the same job as the stronger one. And here you can see some planned icebreaker and ice-going infrastructures. They are planned for polar code A, but they are quite weak. They are PC3 and 5, 6, and so on. So I think really that we should collaborate to get access to heavy icebreakers. And in Sweden, we are doing what we can to try to make our government to build a new strong icebreaker. I should say that there are strong ships. Industry is building. This is a tourist ship. It's open for researchers to come on board. It's a fantastic ship. It's very strong. I don't remember how many horsepower, but it's extremely strong, and it can go. It has been to the Antarctic near the glacier. It goes up and down to the North Pole and so on. But this is what we call opportunistic research. It's not possible to do that kind of themes that we are doing for GOE and AutoMelt, for example, because I think the tourists would be quite bored after 3 weeks in the same area at the North Pole. So this is not an option, I think, even though there are elegant ships. So we try to make our government to build a new one. And here you can see a result from a process that were last year, the Krantz investigation. And it was recommended that Sweden should build a new ship. And we would like this happen. And it should, of course, be climate neutral. No soot, minimum carbon. It should only come out CO2 and water from the chimney. And it should be big, and we should have a large aft deck and flexible use. We should use the technique that we have learned on Oden to have just a large deck and then rebuild her for each expedition, and of course for all year-round use. So I think we have now some challenges for polar marine sciences, and there are geopolitical character and infrastructural, and there is a fragmentation of Arctic cooperation. Russia, for example, will carry on without partners and just carry on by their own. Half of the Arctic is closed for us now. And this has also, I would say, spillover effect of the collaboration in Antarctica. I will give some examples of that. And we have the infrastructural challenges, and that there is a lack of transnational access to heavy polar icebreakers. We have some strong, nice Kronprins Haakon and still Oden, but we need more. Long-term scientific planning is challenged if you don't know that we have icebreakers to put the science on. Here you can see some of the consequences for us at Swedish Polar Research Secretariat because of the Russian war in Ukraine. We had to postpone and stop 2 expeditions. For the land-based research, we have also replanned. We cannot use the Novorossiyska station in Antarctica. No longer the Ilyushin plane will be used by us. We have intensified our collaboration with Norsk Polar Institute, and that is very good, of course, that we, the Norwegian countries, can that are on Dronning Maud Land on Antarctica can work more with logistic and so on. Yeah, I think I have done my time, more or less. You can see what I want. We work even more together, and we need more transnational access to marine infrastructure, and we want to invest more in new icebreakers. And it's also very important that we in the scientific community work for climate neutral techniques for all scientific operations. We in the scientific community cannot be exception. We must try to bring down our environmental footprint as well. Thank you.
So the next speaker is Margareta Johansson, and from Luleå, from Lund University, and she will talk about terrestrial ecosystems and data from that part of the Arctic. Please.
Thank you. And Luleå, it's always the same.
Sorry.
Yeah, no problem. I like Luleå as well, of course. So good afternoon, everyone. Yeah, let's find that one. Now we're all settled. Big button. Great. Yes, so thank you for inviting me. And now we are moving from the ocean up to land. Always nice, isn't it? So, I think some of you have already heard the story, but I am repeating it because I love the story. So let me take you back 20 years, little more than 20 years, in 2001, when we started a network of terrestrial research stations. It was around the North Atlantic. It was an EU project in the 5th framework program at that time. The coordinator was Terry Callaghan. And by the way, now I'm using my time here because Terry said, there will be many of my friends there, I'm sure. So please send my very best wishes. So now Terry sends his very best wishes to all his friends in the audience. We can tick that off. I can tell him I did it, yes. He started this network together with colleagues around the North Atlantic, and it was a 4-year project, and after these 4 years we started to, wouldn't we like to continue to work together? Because then we have started to look at data, how we could harmonize data, making sure to make the data a little bit more accessible, etc. So then after that 4-year project, the research stations, they wrote a memorandum of understanding. We would like to continue to work together. No money involved, no nothing, just we would like to continue to work together. And then in 2011, in the 7th framework program, there was an opportunity to apply for money from the EU to have a network of terrestrial field bases. And we applied, and again, Terry was the coordinator, and we got the money. But from then, we had grown from 9 to, I think it was 34 stations or something like that. And stations had joined the network without any money. The only thing they thought was, it's good to be visible together. We will have this one-stop shop, and it's easier to be visible in a group than separate in all those places. So we continued 2011 to 2016. We have Interact 1. And then from 2016 to 2021, it turned out because of the pandemic, we had Interact 2, and we are now running on Interact 3. That is currently funded until the end of next year, but most likely we will have another year because of COVID. But we have grown from 9 to 90 research stations. And as you can see, a pan-Arctic coverage, which we were extremely proud of last year. But as with all good stories, now we have to pause our collaboration with half of the Arctic. So we are now down to 69 research stations, as we had 21 research stations in Russia that we were collaborating with. But let me emphasize that we are pausing our collaboration, and we really hope that someone will get their act together quickly so that we can continue to collaborate, so that we can actually look at the Arctic and not just half of the Arctic. Anyhow, so the research stations, You can learn more about them, all of them. They are everything. I mean, Katarina was talking about those giant ships, if I may say. They are big. This could be anything from research stations that can accommodate maybe 10 people or so, up to more than 100 people. So they really vary in size, but they have to be able to accommodate researchers, and they have to have monitoring. That is sort of the criteria for being part of Interact. So you can read about it on our website, where all the research stations are presented. We happen to have a Norwegian station there highlighted. And then, of course, you can go into our station catalog, the nerdy travel guide for all the scientists. Where am I spending my next summer? Ta-da! Just flip the pages and you will be super inspired. And then, of course, if you're bored a Friday evening, why not play the Interact card games and learn all about the research station in one go, huh? Win, 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 win situation. You can also learn about the research that is ongoing at the different sites. We have a GIS system where all the research and monitoring that is ongoing at the sites are presented, and we also have it in a paper format if you prefer to do that. So Interact has been a lot about providing access. Half of our budget in all the Interact projects have been used to make sure that scientists from everywhere can access the Arctic, the terrestrial Arctic. So we've had more than 10 years of access to the Arctic that we have provided since 2011. We started off with something that was called transnational access. Katarina was mentioning it before. It basically means that the scientists can go to a research station and they do their research there. They get the accommodation and travel for free. You have to have your own salary and things like that. But at least you can go to the research station and do your research on the cost of the EU. We started off with transnational access. Then we added something called remote access. And this is environmental friendly. It means that it's actually the staff at the research station that can do things for you. So if you have some research that is not rocket science, if I may say, maybe digging down a tea bag of litter or whatever, something that anyone can do, then why should we spend all that carbon by having a scientist go into the field? We might as well just have the staff at the research station to do the things for you. And it has been especially useful now during the pandemic, when we have not been able to go to the research sites if the stations are open. In addition, there is something called virtual access, and virtual access is the access to the real data. So if you are a modeler, for example, you're sat in your desk and you need data from the Arctic, go and have the data. It's available online. So we started off with access to 20 research stations, and when we started Interact 3, we had 52 research stations in all Arctic countries that provided transnational access. So scientists could go to all the countries and apply for everything. Now we're down to 39. Yeah, for now, but let's be positive, and maybe in the future. We have had more than 950 user groups applying for this transnational access. That means that there is a lot of people that want to go and do research in the Arctic, which is great. And they have applied for more than 44,500 person days. If we put that into years, that's if we would put one person in all these years, it would be 122 years. Has to be a very old person, obviously. Yeah. Anyhow, we have supported sort of little more than half of the number of user groups that have applied, and more than 15,000 person days have been granted so far. So, and yes, very quickly where we're at now with Interact 3, we have in total 6,500 days that we are offering at 39 stations. As I said, there were more before, but now it's 39. We've had 3 calls, and there is one ongoing. Would you like to go to the Arctic this summer? You can still apply another week on our website. Just go and apply. And yeah, you can see the statistics. But there are 78 projects that have been conducted. There have been 11 postponed, and that is mainly because of COVID. And then we have had to cancel 10 projects, which is only due to COVID and then the war in Russia, unfortunately. And of course, there is an outcome of all this research ongoing. So we have had more than 200 papers that have been published as a result. There is an online course that is given, and I think there was 5,000 people that have actually attended this. Not everyone took their exam in the end, but very many people have attended this online course. And then we have presented, you can see on the left-hand side, there is Stories of Arctic Sciences. There are 2 books that have presented where you can find and read about the transnational access project that has been ongoing. And of course, one of our favorite projects that has been ongoing is the one that found actually a new bumblebee species in Alaska, the Toolik Lake Research Station. And you all know what it's called? Bombus Interactive. Huh? How many projects have got their own bumblebee? Not that many, I would argue. Anyhow, and this is our virtual access portal. So when you would like to go and get access to the data, the real data, then you could go to the data portal euinteract.org. And we have so far this year had 4,500 users from 136 countries. So obviously there are people that can find the data portal, which is brilliant. But we want more to use it, of course. Interact is also working on improving station management to make sure that when the scientists come and do the work, that it is as safe as possible. How do we reduce the climate and environmental impact? And science, we want to promote science and international collaboration. As a result, we have created a lot of handbooks. I'm sure if you have been to big meetings in the Arctic, you have seen I wasn't bringing them here because it was a little bit heavy, but yeah, there are books around and they're also available on our website. In addition, we want to prepare the scientists that go to the field. So we have prepared field book planning handbook that you can read when you're at home, and then the practical field guide that you can bring with you in the field, and making sure how you can make it as safe as possible and what to think about. Because if you go to a really remote place, you don't want to figure out that, I should have brought 3 extra batteries. It's a really good thing to do beforehand, and that is what you can read all about, and where to put up your tent, etc., to avoid things. Yeah, and then as I said, we have the Interact GIS, and we also have an overview of Arctic permit systems, which I think can be very helpful for scientists. It might be easy to come to Sweden and Norway, but there are always permits that you need to have, need to look at, and they are different from all the countries. And we have tried to put together an overview so that you can easily find all the links and think, see what you need to do before you go to different places. And then providing robust data for decision making. I'm not going to go into details about all those things, but what a scientist wanted to look at with this data was to see how well the Interact stations reflect the changes across the entire Arctic. So, I mean, we had 90 research stations. That's a lot of research stations. Do we cover the full environmental envelope of the Arctic, or what does it look like? And what this scientist did, so he looked at these 2 bars that you can see in the middle. For let's see, we have air temperature, precipitation, snow accumulation, and soil moisture, just as a few examples. And the closer the bars are, the okay job. Can I say like that? No, I can't. The more okay. Thank you. The more okay is the sort of how well the Interact stations are actually representing the different regions and the different environmental envelope. And in general, the Interact stations do a good job to cover the whole environmental envelope of the Arctic. Precipitation is an example, but everyone who has been measuring precipitation knows it's a pain in the ass. So I don't know if it's because of that or just and the same with some ecosystem parameters that in general it's also doing okay, but not with the leaf area index. But apart from the leaf area index, the research stations are actually covering the environment. Which is a good thing. And that was, of course, before when we had the whole 90 research stations. Let me just emphasize that we are not covering the whole Arctic anymore, and not the whole environmental envelope, of course, as a consequence of that. We are also working with ECMWF, yeah, you know, European Center for Medium, blah, 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 blah. Now I'm looking at Thomas because you know the full name, but never mind. Weather forecast, it ends with something in between, medium, blah, blah, blah.
Medium range weather forecasts.
Yeah, round about what I said. Thank you, Thomas. So, but one of the things that if you're looking at predictions in the future are the extreme events. They are very, very difficult to predict, and we have been working together with them and with the data from the Interact stations to try to improve some models and just look at what are the biggest problems and how can we improve them. We're also working with industry, and both we have been working with AFRY, which is a Swedish company, but it's sort of in all countries everywhere, and both with drones to develop new my brain died. New equipment for drones to measure new things, but also with artificial intelligence. How can we make it more efficient to get the data from the Arctic? We have an example here from the Taffala research station in northernmost Sweden that has a lot of diaries that has sort of, okay, this guy said, I stood up and made some porridge and blah, 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 blah. And there might be some interesting thing as well, not just making the porridge, but there might be some environmental data. And then you can train the system to get this information out, which has been done. Also quite common that you have a camera that takes a footage every day, you take a photo every day, and then again you can train the artificial intelligence to detect different things from each other, which is a good thing. And another one is to detect iceberg detection. Am I up? No? No? Okay, sorry. Just another example. We are also working with the Arctic Council working groups, and one example is to document and reduce the pollution in the Arctic. And how can the research station work with this as well? So AMAP, who has been working with us here, has made some suggestions on what the research stations can do to monitor, but also reduce the pollution. And we are working together with the indigenous peoples. As you know, the Arctic is becoming more and more popular for tourists. And when the tourists come there, we have to make sure that it is in a sustainable way. And who could better tell us what would be a sustainable way than the indigenous people that live there? So we are working together with Niklas Labbe here, who is consulting the Sami people from all countries, and to try to produce guidelines how we can, when you're a tourist, you come to this area, what should you think about? And this is in collaboration with the research station. And then last but not least, we are working on education and awareness. Whatever we find from the research station, we have to make sure that it is sort of passed on the information. And I think the best way to do that is through education and awareness. We have an ebook that can be accessed online with a lot of, it's the stories of Arctic science, so it's an ebook. But then in addition, there is a lot of material for school kids and other things. For example, you have videos showing what the glacier look like when it's when you have climate change and when you don't have climate change. You can explore treasures in the permafrost, you can dig with a spade and whatever. Everything is online. So to access all of this information, you can go to our website, eu-interact.org. But of course, you can also find us on Facebook, Twitter, and Instagram. So thank you.
Then we switch over to the third talk, which is by my colleague Lars-Otto Reiersen. By the way, I'm from the Arctic University of Tromsø, Norway, in Tromsø. And he will talk about 30 years of data through AMA. Please.
Thank you. Thank you for this invitation.
And I will give you the next 20 minutes a short history about the work under the Arctic Council, and especially the Working Group Arctic Monitoring and Assessment Program, which I had the pleasure to design and to lead for 25 years. And it is interesting to see how the development from the Cold War and the very positive way we went through the first 10, 15, 20 years, and now we're back to maybe a Cold War. So first, what is the Arctic? When we started this work, what is the Arctic? And we had a compromise, long discussions with the Canadians, because the Canadians, they wanted to have the Arctic down to 60 degrees because they had permafrost down to 60 degrees. And they wanted to have the whole area, and then we said, well, Oslo and Stockholm and Helsinki is at 60. We don't like that to be Arctic. And then we had the Oslo and Paris Commission for the North Sea and up to the North Pole, and they had an Arctic definition. I'm going here. You see that their Arctic session was this line. Okay, so let's use the same so we don't overlap the work. What we do for AMAP will then please the Oslo and Paris Commission. So this is why you got this very special definition of what was the Arctic, but this is the AMAP definition that we use. So the Cold War, very little connections between the East and the West. When I grew up in Tromsø, what we saw was the military ships from France, from US, from UK, having the soldiers have a weekend in Tromsø to go for beer or so at the bars. And it was Cold War going on, highly military, some fishing and mining activities in the north. This is a B-52 over Luleå. One of them crashed in 1968. I've learned now that we had 8 collisions of B-52 planes in the Cold War, and these have been silent. There are 4 bombs fall down over Luleå. Luckily, no one went critical. And still today, we can see the rest of 1 bomb because of the plutonium we can see in the area around. It's still there. The rest is taken down to Nevada and stored in the mountains. And this is the old Kursk, the old one, not the new one that went to the collision at the North Pole. This is a map I got by chance from the Office of Naval Research. Should never have got it, because if you look into the final one, you don't see this. I'm sorry that this is not functioning, but the red line here, that is the dual line, the early warning system in northern Canada and US with radars. And they are the main source of pollutants in the Arctic. PCB from the instruments, and also some DDT used on the soldiers who were in the area. And the same on all the thing in Russia. I did never come to Franz Josef, no, to Novaya Zemlya, but I went to Anadyr in Chukotka, and we're on the same spot. Let's see. Like this. This is a Russian radar station. This is not only petrol in the barrels. It's lubricants and it's war chemicals. We have seen that on the analysis we made in Russia at the Typhoon laboratory. And they have been, of course, leaking out in the environment. And this is from 2004. And the cleanup by Russian government happened 10 years later. Russia don't have a facility to burn organic chemicals. The only thing, a very common way to do it in the West is by incinerating them when you make cement. But the Russians don't have stable production of that. So we never trusted. So where the Russians took this and where they stored it, we don't know. It's taken down from the Graham Bell Island. So these gentlemen start to talk, and we got the change. We got the Finnish initiative, and we got the Arctic Environment Protection Strategy, where AMAP is initiated. This is in 1991 at the ministerial meeting up in Rovaniemi. This is transferred into the Arctic Council because of Canadian push. They want to have a stronger focus on indigenous people and hopefully also on security. But the US shut down the security and said the Arctic Council shall be without security. That's outside the Arctic Council work. Okay, when this came up, everyone thought that all the pollution we saw indication came from Soviet Union. This is from the globe in Canada, and that was not the only place. So when we came with the first assessment from AMAP in 1997 at a conference in Tromsø, lots of people didn't believe the story we told. So the pollution in the Arctic doesn't only come from Soviet Union. Because we had this, we designed this program to do the analysis of persistent organics, heavy metals, climate change, and we made a very critical quality assurance program. So we have data that couldn't be questioned. And this we managed to implement to provide science-based policy based on science to the politicians. And that has been a success story of what we've been doing in the Arctic. And we managed to get the scientists to work together and use the data available, took away what you couldn't stand behind because the quality was not good enough documented. Animation to show the fast transport of pollutants to the Arctic is the wind. This is from a burning in early May in Belarus. And you can see it takes only 2 or 3 days before the atmospheric station in Luleå picks up the contaminants. And by chance, it's the same wind direction as you had at the Chernobyl accident some years later or earlier. So, our observations platforms, you heard now a fantastic story about the terrestrial stations. We need fixed stations on the ground. We need ships of opportunities because we don't have fixed stations out in the Arctic Ocean. We need satellites, drones, and by the chance I was accessed by the NASA to produce operating guidelines for use of guidelines in the Arctic. We spent 10 years to develop that, and it was approved by the Arctic Council in 2015. And obviously the Russian using drones at Svalbard here a month ago, we have forgotten to follow the guidelines. And that is that you shall warn that you shall use it and run it there. Okay, drifting and moored stations and gliders are new fantastic instruments to use in the Arctic, in addition to your big ships. This is the picture of where we got data to the assessment in 2015. The yellow one is the air monitoring stations. You see yellow ones in Ellesmere Island. Pity that this is not here. On the top of Greenland, you have the North Station. You have in Ny-Ålesund, and you have one in Iceland. And then there's Pallas Station in Finland. These 5 stations are the long-term atmospheric stations we have. All the other atmospheric stations have been temporary, only for 3 years. So then we have the human health, that's the red one. We analyze blood samples from indigenous women and children to see what do they get of persistent organics, mercury, what is transferred to the mother milk during the pregnancy, and how is the effects on the newborn babies. And then you see the green are the same from terrestrial and fish. So there's a big gap. It's the Arctic Ocean. Hardly any data. And we have some yellow spots on the Russian side, and they were paid by me. By the money I managed to raise from Norway, from Nordic Council of Ministers, from Canada, Russia said, well, we let the West pay for the environmental work. And so we did. We said it's so important to understand what is coming from Russia, so we have to go in. And we made the agreements with Russian government, the Roskildromet, and we're allowed to come in and do the sampling in the area. What happened then to 21? All the stations in Russia are gone because the funding from the West stopped. And the Russians didn't have funding. So here we see a big change. We don't have data from half of the Arctic. And there's no data from your stations from the Interact on this, what we're talking about here. This is partly what I said. We have been trying to get atmospheric station because they pick up the fast movement of new contaminants. What's going on here? So it's only this yellow, no, this red, that has been going on for more than 5 years. In Alaska, we have a lot of blue points, but in Alaska, you have this conflict between science and monitoring. Science is funded by NSF, and when we've done it for 3 years, there's no reason to do it again. And that's a big problem when you're working in the Arctic. That you have a split between the science and the monitoring. Both should be first-class scientific work, but there's a long tradition that the monitoring has been seen as the left hand, and the research is the right hand. Pity, pity, pity. So that's why we have introduced the quality assurance program under AMAP. All right, ships of opportunities. We've heard a lot about the fantastic Swedish ships. Even the Russians have this Captain Draninsin And that should repeat what Polarstern did in 2020, and then they delayed it for 21, and they also planned it to do it in 2022, but it's never been implemented. I was up at the North Pole, drifting station celebrating AMAP 25 years, and the first Russian drifting stations were, of course, military. And then after some time, when they brought it with Borneo, the beginning of a station in March is that they are dropping Chechenian soldiers. You see here, the man in front, that's a Chechenian, and the two on the tent, that's a Chechenian president and a general. So they are training winter war, and they're cleaning the runway. And when that is done, they open up for tourists and scientists. So the tourists are coming up to run the North Pole Marathon. This is absolutely crazy. Minus 20 degrees, and they pay 30,000 euro to come up and run. And they're just like zombies. It's unbelievable. And then you have a few Russian scientists, your old friend, 70 years old, coming up there, diving under the ice, taking some algae samples for a week or 2 or 3. It's fantastic. But the last years, when we landed, the ice here was 1.5 meters. And they said that's the limit for the plane to land at the area. Drifting buoys, well, this is the Argo boats floating. And if we look at the number, back in 2019, there were 114 drifting in the Arctic waters. That's the maximum I could see. It's very little covered by the Argo buoys, the Arctic waters. This is the fantastic story from Interact. It's a fantastic story to get the data from the terrestrial environment. But so far, they haven't provided so much of the data we needed to see the pollution and also for the climate change in the Arctic. So, thematic, where do we want to have the data to go? We established early thematic data centers that could quality assure the data. So for the atmosphere, we used the Norwegian Institute of Air Research, who at that time also was a data center for the European monitoring, from Gibraltar up to the Arctic. So we just prolonged it. And we talked to ICES, if ICES could expand their database for North Atlantic to be circum-Arctic. And after some years, we managed that. The big problem was that the Americans said, yeah, we can take terrestrial and freshwater. It never functioned because of the funding from NSF. 3 years, that was all. So we never managed to get that in operation, unfortunately. Radioactivity is handled by the Norwegian Institute of Radioactivity because the Russians trusted them. So all the data to be used on the cleanup operations in northwest Russia on Kola Peninsula, we managed to get to Oslo. Human health, very sensitive. Very open data about which mother had high levels of PCB or mercury and baby. So the decisions, they are stored at national storage, but the scientists know where to go and who to talk to so we can see the data. There's a lot of strict. And then we started the SEON together with IASC back in when Sweden last time had the Arctic Council. In this room here, we started to say we need an organization who can secure the stations in the Arctic. So that has functioned over the years, but not fully operating. Hurdle 2, we have a lot of data, but dollar. Very often in Russia. At the last Putin meeting 4 years ago in St. Petersburg, I was sitting in a panel with a lot of stations leaders, and they also talked about the fantastic data they had. And I said, well, I heard this story for 25 years. Why don't you show the data? They wanted to sell it several times. And even Vitaly Churkin, who was leading the Arctic cooperation under the Russian leadership for 16 years ago, we sat together and wrote a letter to the Russian government. He was in the Ministry of Foreign Affairs. We wrote a letter to the Ministry of Natural Resources to free the data related to oil and gas activity in Russia. We could buy it. We were offered to buy it to a company in Switzerland. So this is part of the story, working in Russia in the north. And I still think it's still there. The Americans had a problem because a lot of the study they did related to oil and gas activity, that was done by private business. So they couldn't deliver the data unless the private company wanted to give the data. So these are different types of hurdles when you want to see data and have the key data behind what has been done operating by governments and by private businesses in the north. Identification of nuclear threats, you have to come in here and get trust on the Russian side. So what we did was to use, not we, Nordic Council of Ministers asked AMAP, can you start a team and go in and analyze what is of pollution sites in the Arctic, in Kola Peninsula? And because my deputy at that time was Vitaly Kimstash, he was a deputy minister in Roskildromet. So he had trust in Russia. And we managed to build up a team of radioactivity experts. The Russians said no Americans on the western side, no military. So we came there with a small group of Swedish, Finnish, Norwegian civilian experts in radioactivity. Seven people. The Russians came at 25. One of them a civilian. That was the director of Severodvinsk shipyard who constructed Kursk. The rest were military from the Navy. They knew everything. And at that time, this is in 1994, they were so open. They showed us we knew much more about the reactor in the submarines than on the civilian power plant at Kola. And all of this data we took to Vienna, to the International Atomic Agency, and that started the process to clean up the Kola Peninsula. And that's an interest to see the openness compared to what you have today. We had trust in Russia at that time. 5 minutes. Oh, speed up. So we managed to do the job, and we managed to clean it up, paid by Western money. Hurdle 3, academic career. So many times, scientists on a scientific research were not willing to give away data before they had published it themselves first, because they didn't give any credit for the career by sharing data into scientific assessments. So full credit, one author, first publisher, full credit. So here we have something to do. Scientists, young scientists must get credit to share data even before they self-do it. One example, because based on the data we saw, even if it was not circumpolar coverage, what we could see, this is DDT, the DDE, the breakdown product of DDT, in Greenland and Canada, in mothers. And you can see the decrease from the 90s. The first assessment we delivered was in 87. And then you come up with actions. You have to avoid the main source, and that is the blubber of the seals and the whales. That's where you have the good stuff, the vitamins and the energy. You also have the bad stuff, the mercury and the PCB and DDT is in the same place. So we involved the indigenous people to say, how do you convey this? So we can reduce the exposure, but don't challenge the health. But you can see here the success, and this is also the basis for the Stockholm Convention, signed in 1991. Without the Arctic data, you wouldn't have it. The same, now these are some more effects, you can skip that, you can read it. On mercury, you have the same, but this is not only in the Arctic. This is a whale stranded out of Scotland. 2006, it has 1 gram per kilo. It's a world record. This one is so high because it's so near the source. And she had never had, so you see, baby. She was 20 years when she passed away. So this PCB pollution is not solved because of so much PCB has been used and will be in the environment for 100 years. Mercury, the same. Studies, we had detailed studies on the Faroe Island, so that on newborn baby, there were fine motoric problems after 2 weeks after the birth. If the mother had eaten whale meat twice a week or more, and it was irreversible after 7, 14, and 22 years. And this is the basic for the Minamata agreement. Reduce the use and releases of mercury. Industries lack openness. That's the fourth hurdle. Please start moving here next to me. Tox testing of new chemicals is missing testing under low temperature. What is with the breakdown products, and they're not willing to give away how to analyze things. So we, as environmentalists, are running after the industry, just like the man in Sweden who found PCB first time. He forgot to turn off the GCMS. So we are coming, the industry is always in front of you. And one of the problems is the test system. The test approval. Many companies go to Southeast Asia to test new chemicals, and they have easier test programs to get it on the market. And if it's first on the market there, it's all over the world. Let's skip it here. Okay, from science to policy, radioactivity cleanup, good advice to Arctic people, the protocols I mentioned, and also we played into the UNFCCC. But we were not successful on it because IPCC had strict restrictions that for the polar area, no more than 15 pages. So Antarctica, Tibet, Alps, and Arctic should be squeezed into 15 pages. So the information we had from the Arctic never managed to come in as it should have. This is interesting. From a substance, you have clever chemists can produce a new market product. Goes easily. But if someone sees that there's something problem, you have to document it. So the time from producing to the sea and get the problem, it takes 30 years, 20 to 30 years. And then you give 5 to 10 years time to implement new regulations. So this is a big problem on the pollution side. Okay. The third Arctic Ministerial meeting had not looked into this problem. It's on their agenda, but according to Jenny Basement, they never discussed how to go into this data sharing, to get data shared faster and better between scientists and countries. There's no credit for sharing data. So this is how to improve it. Countries to secure more long-term research and observations in the Arctic, governmental and private institutions to apply more open access to data, and the academic career system credit data sharing on co-productions of assessments. So the submarines, the nukes are back in the Arctic, and it's not only Russian and Americans and UK and French. You also have Chinese and Indian. Thank you.
Thank you very much.
My name is Mikael Tjernström, and I'm going to try and guide you through the last session of the day. If I'm sounding a bit stuffy, it's not just because I'm an old professor. I also have a cold, and I have to apologize for that. So this session is about forecasting the changing ice, ocean, and weather conditions. Forecasting weather is that's an inherent coupling, but I think forecasting can be used to mean a lot of different things. And we will be hearing 3 presentations with some time for questions after. And then in the program, there's a whole hour worth of panel discussion. If we keep going for an hour, I'd be happy to stay here on the floor and guide you, but otherwise we might round off a little bit earlier. The first presentation will be by Jörn Kristiansen. Jörn got his PhD in Oslo in 2004 and has done some interesting work on cosmic rays and climate. And he's also the EAR person. EAR is probably as popular as a weather app as MHI or other weather apps, and Jörn is behind you. He's now a director of research at Norwegian Meteorological Institute, and he'll be talking about developing reanalysis and weather prediction services for the European Arctic. Please.
Okay, thank you.
And I'll give you 5 minutes. And all speakers, when you use the pointer, point at that screen.
So thank you for the invitation. It's really nice to be here. It's first time this academy, and really like what you've done to the place. Okay, start. Yes, as Mikael said, weather forecasting is what we do. So I'll try to say a few words how we develop reanalysis and weather prediction. I'll say a few more words about what the reanalysis is also. And why we also focus on the science for services. Why is this important for us? I think some of the things that came up in early discussions about infrastructure, sharing data, will be touched upon also, and we can come back to that also in discussions if I get some things. So the Norwegian Meteorological Institute, the basis is more or less so the National Meteorological Institute. Its main mission has been since we were established 150 years ago, is to deliver reliable and accurate weather forecasts to safeguard life and property. So that is sort of the mission. That's why we were established. That's a service that is still very much the most important things we're doing. And it's not getting less important with climate change. We're seeing weather conditions we haven't seen before. It's very important to forecast and prepare and help people to take good decisions and also make good policies. So numerical weather prediction, what is it? Well, first you see this young man. I didn't realize it, so I had to look up when I prepared for this presentation, but you see Stockholm. So this is William Berknes. He was in Stockholm, I think he came here 1883 and was first sort of associate professor and then later on a professor at technical high school or university. He combined the laws of physics and mechanics and sort of solved the problem with the forecasting. His work that led on to this paper in, I think it was 1904, must have been sort of, he was going around here thinking about these things. So it's nice to be back where he started. He was inspired by medical science, so that's why he uses terms diagnosis and prognosis. So he solved the laws of physics and the mechanics and realized that we need a good initial conditions, a good diagnosis. We need to know the weather at a specific point in time. So we need observations, a lot of observations. So then you have a diagnosis, and based on this, you can use the equations to look forward in time to have a prognosis of the weather. On top there, I try to illustrate some of these processes that are ongoing, and it's a lot. At some point, there was perhaps a thought that it could be sort of spectral gaps. You could divide processes in terms of their size, but there isn't. So it's a continuum of processes, which just makes it really challenging to predict the weather because very much of these small-scale structures are influencing the weather. The butterfly effect, for instance. You see, I sort of highlighted reasonable accuracy, but William Berknes already said this, that you need to have reasonable accuracy both in the observations and in numerical equations. He did not think about the butterfly effect. That was Ed Lawrence some 60 years later. He also had the problem of storing data. So when he ran experiments and it was computationally expensive, he saved some data but with less precision. So he then reran and got a different forecast. And that got him thinking. So that small perturbations, small uncertainties in observations, in our understanding of the physics can lead to completely different weather forecasts. So sometimes the forecasts on E are not 100% correct, but that's sort of the chaotic nature of these nonlinear equations. And we need a lot of observations, number of observations. If you have that, we can predict the weather in a 3D-dimensional way for the next hours, days. That's the main purpose of the Meteorological Institute in Norway, but also weeks and seasons ahead. And all of these small developments, there's a lot of small developments all the time. A number of people have contributed to this, can be summarized as a quiet revolution on numerical weather prediction. I mean, how many of you in this room are using the weather forecast on the apps today and are trusting them? I mean, it's really amazing. So all of these small developments, there's not, perhaps a few, but not very many sort of big breakthroughs, but all this small work, taking all these different instruments, getting small incremental improvements, have gradually built up to this, the status we are in today. A really good paper, by the way, so that's something you can read tonight. And all this, as I said, that leads on to this year. So a lot of science, a lot of computing, you get very simple weather forecast, like this one for where we are now here today. And I took it out yesterday. I think it's more or less correct. We'll see when I get out afterwards if it's raining. This is updated every hour. No human intervention. We stopped that in 2013. because the humans are not really producing anything to the automated forecast. The human thinking, the human understanding, the way we optimize the forecast, how we use observations like citizen observation, if this is of course very important, but in order to forecast the weather and update as soon as we have new information, we need to fully automate the weather service. When you go to the Arctic, we have a dedicated model system called Normark. The first bullet point, I think Thomas will touch on in the next presentation, that's the yacht project. This model would not have been existing if it wasn't for the international collaboration led by Thomas called PPP. It would also not have been happening if we didn't have the support of the Research Council of Norway with funding. So it is inside this blue domain. It's 2.5 times 2.5 kilometer resolution, so that's between the grid points. It runs for 66 hours into the future and updated 8 times per day. Cutoff might not mean so much to you, but it's basically how long we wait for the observations. So the first weather forecast on ENIAC, it took about the same amount of time as real time, as the wall clock time. So it didn't really have much to say to prepare for the future. But in order for a forecast to be relevant, it must be be available before the real time and wall clock time. So we wait, and the waiting is a compromise. How long can we wait in order to be relevant, and how long can we wait in order to get in as much observations as possible? Because there is the delay once the observation is taken and to the system and so on, until we get it. So every 3 hours, new weather forecast. You see it's a blue sort of a square. We need weather on the boundaries. So there we use the Isnoblev model that was mentioned earlier, the high resolution that gives the weather on the boundaries. And weather forecast and the way we're living is very much influenced by the surface, different characteristics, whether it's farmland, ocean, forest, snow, sea ice. So we need a good surface model underneath. Also the soil, the humidity in the soil is super important in terms of forecasting the weather. And also how they feel the weather close to the surface where we're living. So that is important. This cycling means that the most recent forecast is used as the first guess for the next forecast. So we correct the forecast every 3 hours with observations. So we have a first guess from the previous forecast. We take in lots of observations, see how much these two differ, and then correct and run it again. There's some mentioning of the observations we're using. Someone mentioned Nordic collaboration. 2014, if you see this sort of gray square, 2014, Norway and Sweden were the first countries in the world that collaborated between national Met Institutes in running an operational weather forecasting model. Later on, as Finland has come, and also now Estonia, and in a couple of weeks we'll talk to our Latvian colleagues. But it made a lot of sense to collaborate on this main domain. Other thing to notice on the left figure is this coloring. The coloring indicates the typical errors you find with the forecast as a function of latitude. Green, not so large forecast errors on average. The more reddish, the larger forecast errors. You see there are some challenges in the Arctic, and try to list some of them there. Availability of observations and the quality. Snow was mentioned. So observing snow is super difficult because it's blowing, and basically the observations are not correct. You need to have some correction factor. But more about observations. The Arctic is, of course, has a lot of snow, ice-covered surfaces. That's a specific challenge. The uncertainty in the physical processes. I think Mikael is working on this stuff. The mixed clouds, stale boundary layers, super difficult, still not solved. These are really challenging our ability to forecast. And also small-scale processes that perhaps is not so frequently observed and experienced on lower latitudes. So this is sort of an image. You can imagine it's Svalbard and one place they are preparing for nice weather, and just around the corner it's more windy. This calls for more, in our view, a more dedicated forecasting model for the Arctic. This slide is from Harald Sodman, he's a professor at University of Bergen. We're working together in the alertness project. This is a nice logo. He compared sort of doing research on numeric weather prediction as operating on a live patient. And the thing I tried to make there is that we use operational infrastructure as a research infrastructure. The operational infrastructure you see behind Yr, what's under the hood of Yr, that's also our research infrastructure. So my researchers, not me, I'm too old, or incompetent, but they take basically the operational system, they check it out, and they work on that, make some improvements, check it back in again. And that goes rather fast. There's not too much formalism in it. So you cannot sort of work on a sort of dead person. I mean, it's a live person, and you need to keep him alive. Sometimes you have some sort of bumps. So in the red line is indicated forecast the error. So we want it to decrease. But sometimes it's actually necessary for it to increase in order to decrease later on. One sort of very easy example to show this is compensating errors. There's a lot of compensating errors in these numerical weather prediction systems because they're huge. There's code written in Fortran 77, so there you can see. So a lot of legacy. So if you prove something, one process is, there's a Michael go and improves the mixed phase clouds. Then perhaps he reveals that there are the errors that were there before were compensating some other errors. So these new errors are then exposed. For us as an operational center, they're not so super keen on the forecast they're increasing. But from an academic side, from Harald perhaps, it's necessary in order to improve later on. And then we need also some sort of the tools, metrics, I'm calling them there. But it's basically to open up the model, to look inside it, to see what the physics are doing, to see if the radiation scheme is compensating too much to the turbulence scheme, and vice versa. These tools are super important, but also a bit difficult and not used that much. So we had a PhD student that Gunilla is sort of challenging next week, Marvin, that has really used these tools to improve our understanding, and he really did. These tools are, of course, much more attractive, not of course, but they are more attractive to the academic side than outside the operational center. But for us, for the academia to embrace and use this infrastructure as a research infrastructure, we need to help them and need to facilitate. Because this is a sort of, this is a Ferrari. This is super tuned to deliver weather forecasts super fast. It's not a multi-tool car. So it is not fit for the academic research, but we really need to embrace it and get the academic side to help us to improve the understanding of the processes. And then we compare the observations. This is what I call a simple schematic. But it's from Ålesund and Sodankala. So in black, it's observed cloud cover. So observations cloud cover, and perhaps as most observations, is challenging for what do you actually observe. Do you look up into the sky and see a large fraction of the sky and see some clouds, or do you measure with some instrument directly above you? Either way, you have to compare it to a model which has its characteristics. But anyway, in blue is our market model, and you can clearly see that it prefers 0 or no clouds or overcast. Whereas in reality, it's a bit more mixed. And also you compare to other models. So this is one tool that helps us to improve. And I think Thomas will touch about this job site MIP later on. A service should come from a user need. And one user need is this sea spray icing. It includes some pictures and also a fatal accident there that shows the relevance. This is Oslofjorden, so you probably won't expect too much icing, but it's actually occurring also on more in the southern part of Norway. So a warning service on sea spray icing have been developed by one of my colleagues in his PhD, Eirik Samuelsen. I think the novelty here is that it's fully automated. So based on our forecast from the weather model, based on the model's forecast from a wave model, it's automatically producing the sea spray icing index and warnings. So every time a new forecast, we can update it. You don't have to have people on shift checking this all through the night or to the weekends. We can give this warning service quite quickly. And another nice thing is that as soon as Eirik has improved this research, we can quickly implement it into the operational system. I think I'll skip this in interest of time. Reanalysis is more or less the same thing as numerical weather prediction, so that's a nice thing. So the diagnosis of Wilhelm Bjerknes can compare to the analysis. Reanalysis is that you go backwards in time. Two things that are advantageous is that you have access to more observations. And I mentioned this cutoff. This doesn't apply in reanalysis. And also you have this consistent time series. You use a sort of fixed model version can run it for several tens of years. So you can get a consistent time series, and you can call it maps without gaps. So it takes observations, it takes our understanding of the physical system, the dynamics, and basically give us a good description of the climate. So typical global, and this is one of the most used data sets in geophysics. On the left is the global reanalysis from ISNOBLEF, ERA 5. On the right is the Arctic reanalysis called CARA. Both are funded by the Copernicus Climate Change Service. In the middle is some sort of simple schematic on the benefit of having a high resolution reanalysis. Both of these have in common that we use the operational weather systems, weather forecasting models as the basis for analysis. So it's a very short transition for our part between the reanalysis and the weather forecast. Reanalysis improved, we can take the improvements into the operational system and vice versa. I mentioned the cold surfaces. You might not think it, but until very recently, there were no snow on the sea ice in the NWP models. There's some observation there from a field campaign taking the sea ice temperatures. On the top, you see the number of different reanalysis systems. In the solid black line is observed temperature. The redder, the larger the bias. In the bottom is our operational system. In the second to last row, called row S, is where we introduce snow on top of the sea ice. We took a multi-layer snow scheme and put it on top of the sea ice, and the biases were removed very quickly. So this is introduced in the CARA and in our operational system. And when I approached Yuri Batrak about this implementation and the results, I think it's Nature Communications, whether we can consider putting it into the operational configuration, he just looked at me stupidly and said, it's already in there. So it was implemented long before the publications were out. And the sea ice is not only characteristic by its surface characteristics, but it's also these leads and small-scale structures. This is just a simple experiment we did, or Yuri and Malte, but they simulated on the bottom right there some small-scale structures and the impact that had on the weather forecast. The more reddish, the larger the impact. So you see here in this example, the more impact on the wind than the temperature. And the reason we think that the temperature is less affected is that there's not a responsive sea surface underneath it. It's more static. Observations. Just briefly mention observations. There's a lot of observations in the Arctic, remote sensing that is. So on the left, you see, as been shown with others, very sparse conventional observations. Conventional is radio sounds and things that are mounted on the ground. But in terms of observations, there's a lot. So the top row, you see microwave observations, and the polar orbiting satellites, of course, cover the Arctic very well. On the bottom, there's an experiment of assimilating, using these observations to improve the forecasts. On the left is the summer, on the right is the winter. So you see the scale, so the more like yellow and greenish, the smaller the errors or the bigger the impact observations. So in summer, clearly the microwave have a lot more impact during the winter. And that's because it's much more challenging to get the information from these channels during the winter time. So that's one area of research that is super important. And one thing we can do is to use observations from the window channels. So window is basically where the satellite is seeing all the way down to the surface. So when they can see all the way to the surface, they can see something about the surface characteristics. If you use that information, you can also use more information from the other satellite channels that are observing closer to the surface. And yeah, just half a minute on this. This is a recent study from Kjetil Isaksen and others that took observations, also contribution from the Russians, I think, and looked at the development of the increase in the surface temperature in the Barents Sea area. So the full coloring is the last 20 years, and then there are different time periods. The conclusions was that the warming in the Arctic in this area is much larger than previously known. So the global and the Arctic have a much smaller increase than in this area. The other take-home message was that the CARA dataset was very much replicating this warming to a larger degree than ERA, and also quite close to the observations. And that is the summary, which you can read later on.
The next speaker will be Thomas Young, who is now a professor in physics of climate dynamics at Bremen University, and also the head of the climate dynamics group at AVI. Thomas got his PhD in Kiel in 2000 and spent 10 years at this agency with a long acronym, ECMWF, and has recently been leading the Polar Prediction Project, and I guess we're going to be hearing about that.
Okay, yeah, thank you very much for the invitation. So thank you very much for having me. It's a pleasure to talk about polar prediction, past, present, and future. And as Michael has indicated, I'm giving you a bit of an overview of what has been accomplished in one of the major initiatives in this area that has been supported and run by the World Meteorological Organization. And you know, me being the chair of the steering group of that Polar Prediction Project, probably this is my last public presentation in that role, and it's a bit of an historic moment here, okay, to celebrate, I suppose. Okay, so I run you a little bit through that polar prediction story, okay? And you know, those who have seen presentations of me before, they know that I like to start with the following time series, okay? It's iconic and it really doesn't cease to amaze me, I have to say. That shows the extent of Arctic sea ice in September as time goes on. And what you notice is that, you know, things started to decline very slowly, and then, you know, around the 2000s, things really sped up. And I think it's fair to say that at the end of the 2000s, I mean, certainly WMO woke up to that, and they realized that an effort is needed in order to advance predictive capacity in polar region, which was limited at that time, okay? And that's basically, I guess, one of the reasons how this Polar Prediction Project and then the Year of Polar Prediction came about, okay? Now, I was tasked here, it's 11 years ago, was in Geneva, the kickoff meeting. So I left this center, ECMWF, the European Center for Medium Range Weather Forecast, and took up the professorship in Bremen. And, you know, they thought it's a good mix, okay? Sort of, you know, someone who knows weather forecasting, going to a Polar Research Institute, you know, and they offered me the job of chairing this. And I have to say, this was probably one of the most productive meetings I ever had, because the plans we developed, I guess, most of this actually materialized over the following, I don't know, 10 or 11 years. And, you know, you see someone, you know, Gunilla was there as well, and you may notice some other people as well. And there's a mission statement of this Polar Prediction Project, and perhaps the radical bit was that the weather people went coupled, so, you know, from weather also to environmental prediction, and also in terms of timescales, going from weather also to seasonal, which are, you know, usually considered more climate timescales. And what we realized was, you know, not much was done in terms of polar prediction back then, so the task was quite big, and we needed sort of a longer and massive effort. At the same time, we realized, you know, if we do everything, we can't succeed, so we also needed a focus. And this focus was what we called the Year of Polar Prediction. And initially we thought it would be just one activity of the Polar Prediction Project, but at the end of the day, it turned out to be the activity, and probably the Year of Polar Prediction is now better known than the Polar Prediction Project. And again, you know, here you see environmental prediction, polar regions and beyond, and then, you know, concentrating on a certain period. I think sort of for future activities, it's quite interesting. You know, this came in different phases. There was a preparation phase, a core phase where, you know, special experiments were carried out, but we also had a consolidation phase. So years were allocated for analyzing the data. Okay, and this was picked up by funding agencies, and I think it also contributed to the fact that you know, we had a few cool outcomes here. Now, I have just limited time today to give you a bit of flavor of what came out of this, but there's a bit of a more comprehensive summary here in a booklet that's available from the website. And, you know, if you don't find it, just drop me a message and I'm happy to send you the link. So there you get some, you know, quantitative indicator, but you also get a number of success stories that, you know, I won't be able to tell today in full. So let me get a few examples of what has been achieved. And let me start with sea ice prediction, okay? And there was a very, I think, quite interesting and influential paper by Lorenzo Zampieri, who looked at the predictive skill, our skill in predicting the location of the ice edge, okay? And you see here on the y-axis the error in predicting ice edge, and on the x-axis you see lead time, all the way going to 45 days. And there are two black curves, which are the reference. I mean, one is shooting up very quickly, so very quick error growth, and that's if your forecast is persistence, the ice edge doesn't change. And the other, that's the horizontal line, is your forecast is climatology. Okay, and then all the colored curves are the results from different forecasting centers. And I don't want to go too much into detail, but what you see is that the curves are all over the place. Okay, there are some modeling systems who didn't have even skill at day one. Okay, whereas there are also forecasting systems like the one from ECMWF that have really sort of skill beyond what could be compared by sort of trivial reference forecast all the way to 45 days. So, and I think that the situation didn't really change in the meantime. I think that still describes fairly well the status quo. So sea ice forecasting in a way is still in a premature state. And I think the good news is that the prospects are bright. You know, there is scope for significant improvements in our ability to predict sea ice in the Arctic and the Antarctic. The Antarctic picture looks very similar to the one here for the Arctic. Another example of sea ice prediction, and there I would like to feature this SIDFEX, the Sea Ice Drift Forecast Experiment, community effort to explore the predictive skill of drift of ice, okay? And at lead times from day to a year. And yeah, forecasts are made for both, in this research activity for sea ice buoys, but they also took Polarstern during the Mosaic expedition and mated sort of the flow of the Mosaic expedition as one of the target of this experiment. And I have to say that most of the numerical weather prediction centers contributed to this and provided on a daily basis, they still do that today, forecasts of the drift of Mosaic back then, but also of certain selected buoys right now. Now, very briefly to where we are on this. So you see basically the error in sort of predicting, the error you make in predicting the drift. The larger the value on the y-axis, the worse, the poorer the forecast, versus lead time on the x-axis all the way down to day 10. And basically you see two clusters of curves. One is the upper one. This is sort of trivial reference forecast, sort of your prediction of the drift as it doesn't drift, it persists. Or it drifts with the drift it had before, because these are trivial forecasts. And you see that all the forecasts, the dynamical forecasts with our operational systems clearly beat those benchmarks, indicating that there is skill out there in predicting the drift on weather time scales. Actually, the Mosaic expedition was a very interesting use case for SIDFEX, because they needed for tactical decision making, they needed high resolution terrasar data, and these are very heavy and large, and you have limited bandwidth in the polar region, so they had to cut it out and ask need to specify which area they wanted to have. And SIDFEX went out and helped with their forecast, and here's a summary of those who made the decision. And they concluded that because of this effort, our hitting rate was about 80 to 85, so that they got the right map that they needed for decision making. And they assume, and from previous experience would say that, otherwise, without the drift forecast, the hit rate would have been more like 50%. So, I mean, quite some gain, I would argue, in terms of having this information. It was also used, by the way, for, in support of the Endurance 2020 expedition in the Southern Ocean, also quite successfully so. Which brings me to another area, special observing periods. So when we went out there and sort of to plan the project, we noticed, of course, that the Arctic or the polar regions are poorly sampled, okay, observed. And the idea was for certain periods to try to fill the gap that's in polar region as much as possible, and then use this as a basis for experiments that inform us about the optimal observing system and the value of observations. Okay. And we had quite a few, and I mean, in total in the Arctic and the Antarctic, we had something like 10,000 extra radio sonde launches, 250 additional buoys, and other observations. Now, these data were used in what we call observing system experiments to quantify the impact that certain parts of the observing system have on the skill of forecasts. Okay, and this is from a study by Heather Lawrence, and Jörn has shown you already in a slightly different perspective those results. They show basically how the forecast error increases if you withhold certain parts of the observing system. So if you are in the Arctic and in summer and you pull out, you don't use microwave observations, the upper row, you see that the forecast error increases by 10%. Okay, they have a significant impact on the skill. Second comes conventional observation, then infrared satellite, and so forth. Now, the situation is different in winter. Okay, the impact of satellite, sort of the relative importance of satellite data is reduced, and that of conventional observations is increased, and generally the impact of withdrawing the data is reduced. And I think that is one sign that in winter, a lot of the skill that we have in forecasting in the Arctic comes actually from mid-latitudes. In summer, a lot of the weather is internally generated, so local observations are very important. If you look into the winter, a lot of the driving comes from mid-latitudes. And here you see actually the opposite. What's the, by withholding observations in the Arctic, how do forecasts deteriorate in the mid-latitudes that you can see here? There is an impact. It's small, 2 to 3%, but this is an average picture over many cases. But clearly, observations in the Arctic do have an impact on forecast skill in mid-latitudes. That's what we see here. Now, from these studies and others, we have compiled sort of a schematic on sort of how we picture that mid-latitude Arctic mid-latitude linkages work. And that's in a climatological sense. That's shown on the left-hand side. You see the climatological jet stream, this band of high winds, that is here shown in white. And then you see here three regions that are highlighted. This is a region highlighted by the red arrow. That's where preferentially mid-latitude weather influences the weather, what happens in the Arctic. That's quite often associated with intrusions of warm air and mild air. Where you see the blue arrows, these are preferred regions where the Arctic influences on weather timescales the mid-latitudes. Okay, so that's where the information goes in, if you will, and then it goes out. But on average, this picture on the right, and these linkages, these arrows, are quite small. Okay, and then you can say, well, you could conclude from this, if they're there, but the impact is small, you could say, well, it's always there, but it's weak. But what we also found is that these linkages are extremely flow dependent. So most of the time, probably the link is very, very weak. But sometimes there's a certain weather situation that goes along with a strong meandering of the jet stream when this interaction becomes very important and probably even first order in determining weather in certain region. And these are associated with blocking events over Scandinavia and Europe. And then we actually see that during these episodes, the air of mid-latitude origins goes into the Arctic, is undergoing transformation, challenging physical processes, interacting with topography, and then turning around and impacting mid-latitudes in turn. So these things happen at the same time, associated with sort of these events of the meandering jet stream. And I think this kind of mechanism is not necessarily discussed on climate timescales. There people talk about different physics, but I'm wondering sometimes to what degree this is also sort of a physical mechanism that can be translated also onto climate timescales. Which brings me, I guess, almost to my last part on model development. I would like to highlight, I would say to start with, I think in terms of model development, I would say we are sort of nearing sort of golden times, golden times. I mean, I think there are great opportunities there. And one of the opportunities is presented to us by this yacht sitemap, and I think Jörn has shown something on this already. And the idea is here to help people to use data, okay? You know, quite often when you want to evaluate models, you have these cool data sitting in sort of observatories. They probably have all different kind of formats, especially, you know, if you want to have more fancy, you know, non-standard parameters. And then you have your model. In order to bring this together, that takes you weeks, if not months. And in practice, this means probably most people will shy away from doing this because it slows them down in their research and reduces their productivity. And what has been done here, and you know, Gunilla pioneered this as well, is to really say, you know, for a few important sites in the Arctic, we sort of put the data in the same format as you know, for all the different observatories and the model, and then you can really directly compare them with each other. So you know, same format, same data in observations from different sites and in the model, and it hardly gets any easier than that. You know, people can pick it up and do research straight away. And in this way, you know, we can really lower the hurdle of using the data and hence increasing the uptake. And here's a bit of a, you know, some preliminary results on this. I can say that, you know, Gunilla and colleagues, they are currently analyzing the data and are in the process of writing a number of cool publications. Another, I think, cool application, and you know, I may be biased, you know, in terms of that gives us the opportunity really to improve our models in the coming years is an approach that has been recently developed and that uses nudging. So what we take is we take a full climate model, you know, like the ones we use in CMIP to contribute to IPCC, and then in the climate model we start, you know, for certain periods to impose the evolution of the jet stream from day to day. Okay, you know, the jet stream you have seen on the figure. And by doing and leaving everything else untouched, temperature, moisture, the ocean, the land, that comes all from the climate model. But you know, the weather and the evolution is imposed by you know, imposing the jet stream. So what we can basically do by this, we can teach the model the evolution of the weather, and therefore we can bring it into the vicinity of what was observed during campaigns like Mosaic, for example. And here you see the 2-meter temperature in black, you know, from the Mosaic expedition here. And then you see blue and red curves, and these are sort of the temperatures as simulated by a full coupled climate model that has been sort of put on track by nudging the jet stream. And what you see is now these data sets become comparable. Normally when you have a climate model, the climate model has its own weather, you know, and so you don't know whether the differences are due to differences in weather or in, you know, in physical processes. Here we make sure they see the same weather, and you can really diagnose differences in processes. So I think that's a cool stuff, and will be probably quite helpful. That brings me now to my last point. I mean, we have learned quite a bit also in terms of user needs, okay? And probably one of the surprises that emerged at the JOP Final Summit a few weeks ago in Montreal was that most of the people, or quite a few, actually use windy.com. Okay, so this is widely used in the polar regions, you know, in the high north by indigenous communities, but others as well. And that makes you wonder why. You know, what does windy have that it makes it so attractive? And I think that's the parameters that are quite important that are there. But I think it's also the way it's displayed. You know, it's extremely intuitive, and therefore, you know, people can grasp that. And I think, you know, keeping this in mind when we shape our you know, research or evaluation programs, you know, I think that's quite important. Also, in the light that we are developing kilometer scale models that start to simulate some extremely, you know, a small scale and interesting, exciting features. So this is from a kilometer scale simulation in an EU project here, and you see the winds. Okay, we call this here Europe in winds. Okay, and it's amazing. You know, at this 2.5 kilometer resolution, what kind of details you're getting. I mean, look at the Mediterranean Sea, for example, and, you know, but you see, you know, Jan Mayen, you see the wake for hundreds of kilometers. And, you know, taking these type of things and evaluating them, how good they are, for, you know, formulating hypotheses based on this, I think that's a cool way to follow. Now, this is still probably nice visualization on cool and stuff, but you can still say this is not quantitative, you know, science. You know, it's sort of quite interesting. But I think we also start to be able to do quantitative science with these kilometer scale models. And this is from a PhD student of mine, where we looked at sort of how the Arctic Ocean, you know, the surface currents here, you know, the lighter the color, the faster the currents, how they change in a warming world. On the left-hand side, you see the ocean currents in the Arctic in present-day climate. You see hardly any ocean eddy activity. If you go to the 21st century, the 4-degree warmer world, I mean, ocean weather really sort of picks up, okay? And we also understand why this is. Once the sea ice is gone, your sea ice is dissipating. It's just killing off all the eddies. And once the sea ice retreats, all the weather in the ocean can spin up and is not disturbed anymore, okay? I mean, I guess the physics and the effect we know, but I think we are now able to describe this in a quantitative way, with kilometer scale models. And again, I think that's a super exciting and promising to follow. Which brings me almost to my end. So, what's the future? I mean, we are currently, extending this year of polar prediction into 2023. Carrying on with our Southern Hemisphere activities, our model intercomparison and improvement projects, especially centered around the sitemap, and also our societal and economic research applications. And beyond 2023, we're currently working with WMO on putting together a polar climate analysis, predictability, and social science component here. And I leave those final remarks up here and happy to hand over to you for discussion, Michael.
Thank you. The last presenter is Cecilia Mauritsen. Cecilia got her PhD from MIT in oceanography in the mid-90s and has quite an interesting career. She's now a senior scientist at Metno in Norway, but has been the director of CICERO and has worked with risk management and a lot of applied things. And she's going to talk to us about rescue.
That's right. Thank you so much for the invitation. I'm very embarrassed that we are two Met people here today, but I think we have to say Jörn and I represent the Met services at any country, and they just happens to be the Norwegian Met services. Following up on the discussions that were just going on about observations, I just would like to start with one anecdote, if I may. 7 years in my strange career, I got to sail across the Pacific. It was my last oceanographic cruise, and it was on a balsa raft. It was the Kon-Tiki 2 expedition. And we had about 60 instruments on board. We were doing a full, I think, oceanographic a cruise with lots of instruments and observations, and one of them were weather observations. Because in the middle of the South Pacific, the weather forecasts are not flooded with observations, obviously. So on a very small data range, I was sitting there using the codes of the WMO to send in weather information every 6 hours. And the way this works, you send it all into Meteo France in very strange combinations, and they go out to all the weather services in the world, and somehow, magically, it comes back into weather forecasts. And indeed, we noticed that our weather forecast improved when we started sending in that data. And I think that's really amazing. So never underestimate the value of observations, I guess, is my anecdote. All right, let's see. So emergency preparedness at Met Norway. The 3 lines in gray have to do with weather forecast, so that's covered by what Jörn was talking about. But when I'm going to talk about the marine operations, search and rescue, and things that have to do with oceans and ice. So this is the stuff we do when there's an emergency, in addition to all our regular, of course, weather forecasts and ocean and ice forecasts. Now, for Norway, the Arctic is mostly the Barents Sea. Svalbard, a little bit north of there, but anyway, we of course have a huge interest in the Barents Sea. So here is sort of an overview of what the main currents look like. I'm an oceanographer. This is sort of my scale of data, really. But anyway, the models, of course, are amazing, as I'm going to get to. But anyway, there are accidents happen, and they will happen, period. Now, this was happening up on the northern tip of Svalbard, and it's a North Guider accident. It was in 2018, and it was a result of a glacier ice fragment embedded in the seasonal ice cover. Now the rescue operation took place over several months. It was a very complex thing just to sort of rescue this ship. But we work then in such a case with the Norwegian Coast Guard. That's who has the responsibility for coordinating when there is a serious accident at sea. So there, of course, what they do is they go out and they check what's. I realize I can't really read what it says over here. I'm sorry. I'll use glasses now. They, of course, use any kind of way to see what's going on with any helicopters, drones, and satellites, and so forth. And then they want to hear what's the most likely scenario and what are the worst case scenarios, and that's where Met Norway comes into play. So the value chain from data to research to emergency preparedness at Met Norway goes really from the users, such as the Coast Guard. And they gave us feedback. We do research and development. We have about 100 people working on R&D at Met Norway. And then we need observations. I should have put it in triple capital letters. And then, of course, there's the model. And then we go back to all the things that can happen, whether it's a man at sea, it's the regular weather forecast, it's the ship accidents, or it's the forecast of a polar low. That is the value chain. And we also look to windy, of course, and I don't think we're quite there, Jörn, but will windy come, that kind of visualization get into our...
Before Christmas.
Ooh, stay tuned.
And it's also readable by colorblind. Now the plan is to have a new map service that is dynamic on it before the end of the year.
So, I'm sure SMHI already has this, but anyway, if you don't, before Christmas, check ir.no. But anyway, after you have these models that I will get to, for a search and rescue operation, that is basically the physics behind. We need an ocean model, we need an and by that I also mean an ice model, atmospheric model, and a wave model. And you need all those models to go into a drift model to figure out where things are going. And our framework for that is called open drift. But how to make a forecast? Observations. I guess it's been said enough here this afternoon. But really think about this. If you don't know what the weather is like today, you cannot make a forecast. Or if you don't know what the ocean looks today, you cannot make it. There's no way you can do it without observations. You may have a feeling of the light outside or the redness of the sky, but that's observations. You know, you can, and certainly the models need that information. So our observing networks are in situ observations from a wide variety of platforms. And so I'm talking about ice and ocean now, remember. Surface temperature and salinity from anything we can get our hands on. And here's something really cool we have now that we're building up around the coast of Norway, and that's HF radars. And they actually read off velocities directly. In a radial direction, I have to admit, but anyway, it's information on surface velocities directly, which is of course really what you need if you're going to follow something that's drifting at sea. But of course, the satellite data is what can cover the entire globe. And and especially into the Arctic, where the in situ data are much less and frequent in space. So the passive microwave, this is a little 101 on satellite data. And the passive microwave data, they are really the main source of global studies, such as climate studies. So you see the sea ice extent on the left, and you see the seasonal sea ice extent in the middle there. But they are crude in resolution. You see the picture up here. This is Svalbard region and the Tromsø Strait. But we are working really hard at the MET in R&D to get more information out of just the passive microwave. So that's one of the examples here of the resolution you can get by working harder just on that. But of course, there's something that's much higher resolution, and that's the synthetic aperture radar, the SAR data. Now they come in smaller stamps in a way, but you can use the combination of those passive microwave and the SAR data to automate ice charting. We have an ice charting division up in Tromsø that has been sitting by hand for decades to make ice charts daily for shipping in the north. And so of course we try to automate that process desperately. Yeah, I think I had a point more, but never mind. We also get, of course, the SST, infrared sensors on the left here. And then if you add on passive microwave information, which can see through the clouds, you get a much better set of information on the right. Now, to make good satellite data, it's a full-time job for a huge group at Met Norway and most other weather services, I imagine, because these are really the cornerstone of forecasting because you get them real time, so well covered. And then you need to assimilate this into the models, and that's really where you use the. As I said, if you don't have the information today, you can't make the forecast tomorrow. Technically, how you do this is a wide range of ways to assimilate data. As you said, you take all the in situ data, and you work on the satellite data, which you have calibrated with the in situ data, and then you run the forecast. And here is a I have to read what I said here. Well, basically, this is the ice and ocean forecast that lies beneath the aroma data weather forecast that we have. This is a 2.5 kilometer resolution ocean and ice model of the Barents Sea. And interestingly enough, the request for this higher resolution, we usually have run on 4 kilometers resolution, but then there was this Russian helicopter who, well, what's it called? Fell down outside Svalbard, and we were really told to increase our resolution on all fronts to be able to serve such an emergency. So now we look at 2.5 kilometers, and you're starting to see a lot of the eddies and the activities of the open ocean there, and also the ice edge. And here we see the forecast. I hope, is it moving? I think it is. Yeah. It was the ice and surface temperature, surface salinity forecasts just for a couple of days, the 2nd of November. On the left-hand side, it's well, on the right-hand side, you see the ensemble members of the ice fronts yeah, I didn't explain that well. The black is the observations, and the no, the black is the 50% observations, ice cover, and all the red are all the ensemble members of this forecast. And you see, of course, the sharp edge of warm and salty Atlantic water flowing north of Svalbard here. And if we had covered the window further down, you would have seen a similar pattern of warm water flowing into the Barents Sea. But anyway, this is the kind of information that we produce for whenever there will be for instance, an accident. So then I'm moving into that open drift system, which is what we put once we have the forecast and once we know there is a problem somewhere, we have a model, Lagrangian model system to try to figure out either where things came from or where they went to. We have an iceberg drift model in trial right now. We've had fish larvae eggs, we have plastic, we have for a person, we have oil, we have ships, and all of these, of course, are different. Every one of these have a different density, a different property, but this open drift system is sort of continually expanded to account for more kinds of things that might float around. So once the accident is there, and we, for instance, say it's a search and rescue, we go ahead and run this system for that particular site. Now a couple of examples of things. For oil, of course, there's an enormous amount of chemistry going on. I think we have 50 different kinds of oils in the system, and they all break in various ways depending on their surface properties and density and so forth. They sink, they mix. There's a question of what kind of what's it called? If they spray things on to make the dispersion, what's it called? Yeah, well, whatever the oil companies do to make the oil disperse will also be taken into account by this model system. 5 minutes, yeah, I'm there. And here we have made a simulation of a hypothetical spill north of Svalbard, northwest of Svalbard. Norway is actually, I think, the only country in the world who's allowed to make real experiments with oil spills like this. So every year or every second year, all the world's modelers of oil spills come and join these experiments to learn more about how different oils drift. But anyway, this is just one of the things. Of course, it's much more cheaper and simpler to do it in a model system. Another thing is if there's ship drifting, you need to know how big the ship is, what's it made of, what's the wind, wave currents, and so forth. This all goes into the open drift system, which at each time is run 100 times to give you some sort of probability space of what's going on with whatever is the problem. So back to Northguider in 2018. Also there, the accurate sea ice information was, of course, super important because it was in the marginalized zone. So the weird thing about climate change and the fact that the ice is more dynamic, more moving, less concentrated, less thick, makes it even more dangerous. Things move around a lot more, so it's actually more dangerous for the for accidents. What should I say? Yeah, it's the reading. I'm so sorry. I'll jump forward. But anyway, it was a very, very successful salvation operation, and of course the Coast Guard was congratulated, but our job, the Met, is not to be visible, but to be good. So of course it doesn't matter if we're not mentioned, but it's nice to know that we're contributing. And by the way, this is another anecdote. Okay, I got 1 minute. This open drift system, because it's so fast, you don't have to run a huge model. You have the huge model simulation, the physics of the ocean and the ice and so forth. The drift model is much faster to run. So you can use it as a flight simulator with stakeholders who need to understand the situation, the problem. And it doesn't have to be, it can be any problem. I've had a project on a plastic, and we had a huge group of marine litter stakeholders, and we sat in the same room for 2 days and just ran, what if this, what if that, what if that? And everybody went out of the room so empowered because they finally understood a lot more about what ocean currents really mean for drift of marine litter. We cheated a little bit for those physicists in the room. We ran it backwards too, which really screws up the whole well, energy dispersion system. You can't run really energy backwards, but anyway, you still get an intuition about, can it come from England, can it come from there, yeah. So I really recommend using drifters with people and with somebody who can push the button. It's really fun and instructive and much better than any talk can be, because you just talk and talk and talk. Anyway, I'm going to summarize. Accidents will happen, period. The problem with the Arctic is threefold. Well, it's manyfold, but these are the three I picked out. It's data, distance, and change. So I repeat, we cannot create forecasts with the information. In the Arctic, we rely heavily on satellite information, which of course completely depend on the little in situ information we have to improve the satellite information. And we continually in the Met to continue to improve our tools. The best preparation is prevention. Every accident avoided is a victory because it is so damn far up there. And the Arctic is changing. So less compact ice is actually more dangerous, and more activity makes it even more likely that accidents would happen. And those were my